Hello everyone, welcome to the game theory course. So what is game theory? Game theory is the study of interaction. It can be any interaction, it does not have to be strategic. So often people concentrate on strategic interaction since that is natural for us people to think strategically. It does not have to be strategic, as I said, because it also can be that you have certain types of moths or other animals who do not actually think, and simply some moths behave in a way which gives them more resources, and thereby their progeny has more resources, and then they behave in this way which gives them more resources, and thereby their population grows. And there is no strategizing here, but still there is interaction, and that can be studied in so-called evolutionary game theory. So game theory is a mathematical analysis of any interaction. Now, game theory is very relevant. It's very old because, interaction itself has been around, at least on Earth, for at least 3.5 billion years, because that's how old life is. As the thought of what it means to interact and how we should interact and how we can set up the systems. So the theory, it's not that old, of course. It cannot be older than people, assuming that there are no other intelligent species on Earth. But at least the ancient Hebrews wrote about that in the Bible, and there is a nice actually lecture about the problem that Solomonius solved. I remind you that he solved the problem of which woman is the mother of the child, because there were two alleged mothers. And he set up this mechanism that the one who is the mother will, of course, behave in a way which he will know that is the true mother. And without going into that, there is a nice lecture by Wojciech Zawuski, which actually talks about that thing in depth. Another thing from ancient Hebrews is the Talmud, which was analyzed by Uman. And the rule there was, I guess, quite typical for those ancient books. If a man dies, how his inheritance should be divided between, I do not remember, between his wives or between those who were related to him in any way. But anyhow, there was a rule there, and what Uman did, he basically analyzed that from a mathematical point of view, and he gave a set of axioms that would yield the same rule, which of course allows for a nice insight into that. Another very ancient example of game theory is the ancient Chinese, of course, the art of war. So all ideas about how we should fight, how we can strategize on battlefield, they're quite old. They're at least as old as the art of war book, probably older. And since then, of course, there are many new doctrines. And by the way, notice that the military doctrines change with time, because naturally the strategy depends on the environment in which you act. That's true not only in military, that's true in any case. Now at the university, your studying strategy apparently differs from what you had at school. Now, modern game theory, if we are doing this historical review, it actually began with voting models, interesting enough. And it began with the models, for example, of Condorcet. It was in the context of the French Revolution, so that they suddenly needed, how can we vote? They needed to know which voting systems they could establish, and so that they would be efficient. And then there were economical models by Cournot and others, and that was already 19th century. So people analyzed production and competition and such things. And all this took the abstract form of modeling any interaction, the form we are going to study, only in the 20th century. So the form we are going to study is actually very, very young. It's about 100 years old. It begins with von Neumann and Morgenstern. Maybe it's even less than 100 years old. I think it's even less than 100 years old. And of course, since the models of interaction we are going to study are very, very abstract, they have infinitely many applications. So in particular, we can look at all the ancient examples and see what we can tell now about those examples. Well, let's write things down. And I apologize for the quality of writing. That is partially due to my bad handwriting, but partially due to the technological amenities I have here. So first of all, game theory is the study of interaction. Now it can be, as I said, strategic, which we are going to mostly study, or not. Okay, it's quite ancient, so interaction itself is at least 3.5 billion years old. 10 to the 9th years old, at least on Earth. But thinking about interaction, so theory, is also quite old, so the way of strategic thinking it harks back to the Bible, Talmud, the art of war, and there are many other examples. Okay, now one second, let me check. I hope you see well. By the way, since this is a very new setting, please let me know if you think something can be improved. I'm sure there are many things which can be improved in the technological sense. Okay, so then we said that in the modern times, so the modern game theory, it probably, I can say it starts with voting rules, and that is Condorcet. Probably de Condorcet, but anyway. Then a bit later, models of Cournot, so production models. Which can be actually nicely analyzed using the tools we are going to study. That's just an example from our point of view. Production models, and of course the forefathers of, or let's say the founding fathers of the modern game theory is von Neumann and Morgenstern. Well, John Nash He's very famous, but he already was later, so he cannot be, I think, called one of the founding fathers. He simply is one of the people who built it. Okay. And what else to say for the beginning? I like to think of the connection between algorithms and game theory. So an algorithm is something you do, something from the point of view of a single entity, be it a person, a company, a country, or something else, a robot, for example. So game theory can be said called like multi-algorithmization. You have several entities, each one with its own algorithm, and they act taking into account what the others do. So it can be said multi-algorithmization. Now, another thing is that sometimes, and often mostly, we are going to look at agents who actually think. For example, people, or for example, companies. Those who rule companies actually think, of course. And then, if a person has decision power, it does not have to be rational, does not have to be very smart, but some decision power, we can say it's multi-decision. So there is decision theory which deals with how to make decisions, and if you have several deciding parties, then you have multi-decision, a multi-decision situation. So a multi-algorithmization when the parties, of course parties are just entities, they don't have to be political parties, any parties, decide, so when there is some willful act, it can be called multi-decision making. Okay, so we've said that game theory is a study of interaction. It's very old in a way, it's very young in another way, and it's anyhow very important. So now let us move to the next part of the lecture, and I hope it works. It should work. Okay, I think we are kind of back on track. So my apology for the technical problem. And now let us talk about the various branches of game theory. So basically game theory has a lot of branches because you have a lot of practical problems you want to deal with, or you have a lot of ways to model the same problem. So there are many branches. The two main branches, at least in my opinion, that is game theory per se. So when you basically study what is the reasonable behavior to expect in a given condition. For example, in a given economical situation, now that we have a crisis, people are going to buy less, for example. The other branch is mechanism design, and that is basically the dual question. How shall we set up the rules of the system? For example, how shall we set up the laws in a country in order to have people behave in a certain way? And that is actually similar to implementation theory. So those are two very important names, but they are all from the other branch. Okay, so let us write down what we just said. So, classification. And I must say that there are many people who think you should classify game theory in this way or that way, For example, some people think that now we are going to talk about cooperative and non-cooperative game theory. One person can say that non-cooperative is more important, more basic than cooperative. Another one will say no, they're equal or something like that. So it's only my view, not only my of course, but it's only a certain view on the parts of game theory. It's not like it's the only possible approach. So classification, I may say it's a widespread view, but not the widespread view, because there are several. So, okay, so game theory can be divided into, actually game theory per se, what happens in a given system, in a given game, because game models system, as we will see, and the other approach, and that is how to achieve the desired behavior. And that is either mechanism design or, it's not the same, but very similar, implementation theory. So, game theory per se can be divided at least to two parts, which is non-cooperative and cooperative. I will begin with the non-cooperative because that is what we are going to start with also. Non-cooperative. And non-cooperative, let's call it one, is when you have agents who can choose some strategy in order to improve their well-being. So the choice which we concentrate on, the model thing, is the strategy of agents. So we model agents strategies explicitly, because of course you always assume that agents have some strategies. You know what I should write? Not agents, I should write players, because we are talking about theory, so it's better to say players. If we spoke about artificial intelligence, applications would be agents. So let me say players. Explicitly. Okay. So that thing models the strategies explicitly. And there is, of course, cooperative who does something else. So there is cooperative. And that does not model strategies explicitly. What it does, it actually models which coalitions they can form, and given a coalition, that assumes that, okay, they achieve something. So that branch models the coalitions. Explicitly. Okay. Now, now let us talk about further divisions, so non-cooperative game theory. And now I'm talking in a very high level manner, so don't worry if you don't get all the details, since I do not give you all the details. I just want you to have a flavor. The details that we need, we will get into those details later. So non-cooperative game theory can have at least two classical modeling approaches. So the same thing can often be modeled, in two ways at least. So one has, the first way is strategic form. Strategic form, or also called normal form. And here you just say which strategies exist and what happens if a given combination of strategies takes place. So we just models the strategies and the utilities of the agents given each possible strategy profile. Are we stuck again?